while people are joining, welcome to our, I think, season 2 for our SIGCOMM Paper Reading Group. Because I think we started this reading group like in October last year, and I think we try to decide, okay, when is one season, but based on when the next year SIGCOMM is held. So we all I think many of us has been spent a wonderful week in Coimbra in Portugal for SIGCOMM 2025. And so the start, and after the SIGCOMM conference, I think many of us have been working really hard for NSDI fall deadline. So it's a really consecutive tight schedule. So, but after that, I think it's time for us to start the second season for this paper reading group. So since this is a new season, we will start to focus on a more recent SIGCOMM papers. In other words, papers from SIGCOMM 2025. So to begin this season, this meeting, we select a paper called NPC, Rethinking Dataplane through Network-Aware Packet Classification. So I think this the title of this paper really talks about, it clarifies what this paper is about. It's about packet classification. It has been a very important and classic problem in networking, in particular on the data plane. So, but since this is a very classic problem, there has been many very efficient and creative algorithm and system has been designed and deployed. So it's really surprising, a little bit quote unquote surprising, but also pleasant to see this year's SIGCOMM. We also have this paper on this very classic yet very important topic. So I think for this paper, for this meeting, we have invited Boling Zhai, a PhD student from University of CAS for the presenter. And we're also honored to invite Dr. Xinyi Zhang, the first author of this paper, as our guest of honor. So without further ado, we will give the floor to Boling. So Boling, you can start your presentation. And after your presentations, we can we can have Xinyi to join us for a live discussion. Please, the floor is yours. Thanks.
Okay, thank you very much. Good evening. I'm Zhai Boling, a second-year graduate student from the University of Chinese Academy of Science. Today, I will introduce NPC, a network-aware packet classification system. The main idea of this work is to rethink how we design the network data plan by making it aware of traffic patterns. First, let's briefly clarify what packet classification is. When a packet arrives at a device, like a firewall, the device reads a packet header. It took at source and destination IP addresses, source and destination port numbers, and the protocol type. Then it matches this information against a table of rules. It executes the rules with the highest priority among all matched rules. Packet classification is used in firewalls, intrusion detection systems, and software-defined switches. Its efficiency affects the performance of the whole network. Packet classification has been studied for many years. One major type of algorithms use decision trees. The top left of the slide shows an example rule set. The part below shows the rules in a geometric view. In decision tree-based classification, we build a tree. Each rule is assigned to a node. We start from the root and split the rules based on certain features into child nodes. We repeat this until we meet a stopping condition, like reaching maximum depth or having few rules in a node. During lookup, we go down from the root. At each node, we pick a branch based on packet info until we reach a leaf node that gives the result. Existing tree-based methods can be grouped into two types. Cutting-based methods, like haircuts or hypercuts. They split the rule space evenly into segments. This allows faster lookups, but may store rules multiple times, which uses more memory. splitting-based methods like hyper-split. They split the space unevenly. This reduces memory use but may need more memory accesses. The goal is to balance memory access and memory usage. Current algorithms design data structures based only on rules, but in real networks, what matters is how many packets we can process per second. This depends not only on the lookup structure, but also on traffic patterns. Today's methods assume every rule is equally likely to be matched, but real traffic is not balanced. It is highly skewed. You can look at this picture. We studied real traffic data from 2 time periods. For each, we collected UDP and TCP packets and counted packets per flow. Based on the 5 tuple, we plotted the ECDF and fitted it to a parity curve. This results shows that the network traffic is heavy-tailed. This means a small number of large flows make up most of the traffic, while many small flows make up only a little. So few flows are very important. Now, let's use traffic information in the decision tree. Look at the example results on the left. If we build a tree with haircuts in the middle, and if most traffic matches rules 4 and rule 5, this one and this one, then packet for rule 5 must go to level 3, this one, this 2, and this is 3. So they can finally. If we use consider traffic when building the tree and cut first in the x dimension on the right, this picture, then packets for route 5 only need to go to level 2. So we learn we can use both route sets and the traffic patterns to build a better classifier. Next, let's see the design of our NPC system. We combine the rule features and the traffic features to propose the TRD tree, traffic rule driven tree. We also combine the traffic monitor and the packet classifier into one system. The NPC system has 3 parts. The first one is the rule set analyzing module. It has 2 jobs: analyzation features to choose the best structure and detecting rule changes. And the second one is the traffic measuring model. It uses a sketch to find the top key flows in the traffic. And the third one is packet classification module. It has a lookup data structure and an updater. The updater watches traffic and rule changes and decided when to rebuild the structure. At the start, we built the structure based only on rules. After some time, we rebuild it using traffic info. In decision trees, memory use is often high because rules are stored many times. Some rules cover a wide range, so they appear in many nodes. To handle this, we analyze the rule size first. We use the Monte Carlo methods to sample rules and count how many overlaps each rule has. We compute the average overlap count. If it is high, we use a multi-tree structure. Or if it is low, we use a single tree. For single tree, we check the overlap weight for source and destination IP. If the weight is high, we use a splitting-based structure to save memory. If it is low, we use a cutting-based structure for faster lookup. To collect traffic and find top key flows, we use a sketch. A sketch is a probabilistic data structure. It estimates statistics for big data streams using little memory. Our traffic measuring framework has 2 parts: a hash table for collecting traffic and a min heap for tracking top key flows. We also use a matrix to find flows with the most packets. The hash table has D areas, each with W buckets. Each bucket has N entries. Each entry stores a flow and its frequency. For top key tracking, we use the traffic driving stream summary, TDSS, with a min heap and a hash table. Then hash table records where each flow is in a linked list. In TDSS, each node groups flows with similar frequency. This avoids dynamic memory allocation and saves memory, making the system efficient. After collecting the traffic features, we introduce our TRD tree construction approach. When building the tree, the first step is to choose which dimension to split or cut. Traditional methods usually make this decision based on the rule set itself, but in TRD tree, we take both traffic and rules in account. We use two key metrics. The first is a uniformity score, this one. It shows how evenly traffic is distributed across a dimension. The second is a white score. It measures how heavily routes overlapped in that dimension. By combining these two metrics, we can choose a dimension that spreads the traffic more evenly and avoids too much more route duplication. In this way, the classifier achieves faster lookup with lower memory consumption. After collecting the dimension, the next step is to partition the route space. There are two common ways. Splitting divides a dimension into two parts, while cutting divides it into multiple equal-sized segments. Current methods usually decide where to split and how many cuts to make based on the route features. But in TRD tree, we also take the traffic patterns into account. When selecting a splitting point in a given dimension, the TRD tree adopts a balanced strategy. This accounts for both traffic and route distribution. For each dimension, the point P that minimizes the traffic route weight balance dimension is selected to split the dimension. This achieves a better balance between memory access efficiency and the reduction of redundant route storage. If the decision tree is cutting-based, selecting the cutting point is equally crucial. Traditionally, cutting-based methods typically perform uniform cutting along the selecting dimension. However, when considering net traffic patterns, applying more cuts to high traffic nodes can efficiently optimize memory access frequency. Conversely, reducing the number of cuts for low popularity nodes has no significant impact on average memory access time, but instead elevates the additional memory overhead caused by high popularity nodes. Therefore, a function is designed to determine the number of cuts for each dimension by comprehensively considering traffic distribution characteristics. We also design traffic-driven leaf threshold. The TRD tree innovatively employs a dynamic traffic-aware threshold. When traffic corresponding to a node is sparse, a larger base value is used to reduce the number of leaf nodes, lowering memory consumption without significantly impairing classification performance. Conversely, when traffic is dense, setting bins to a smaller value reduces the number of linear search operations and improves search efficiency. In real networks, rules and traffic change, so we designed a monitor that checks the rule changes and traffic changes every little time. For example, per 13 seconds, if changes are big, it triggers rebuilding. And A or B switch strategy. The old structure A keeps working while we build the new one B in the background. When it is ready, we switch to B smoothly. But sometimes traffic may be malicious. So we also have a tech-aware mechanism, burst traffic detection. It checks if new top key flows last multiple windows. If not, it may be an attack, and we delay rebuilding. Traffic distribution flatten detection. It uses the Gini coefficient to measuring how skewed traffic is. If it becomes flatty suddenly, it may be an attack. Our experimental setup is shown in this slide. We compared MPC against 5 baseline algorithms. For data sets, we use both IPv4 and IPv6 for ClassBench and ClassBench NG. In the evaluation, we focus on key metrics such as memory access, memory footprint, and construction time, as well as system-level features like the attack-aware update mechanism and the integration of MPC into open switch. Under this setup, let's start by looking at the most basic can classify packet. For memory access, TLD tree greatly reduces memory access compared to original algorithm. You can see in this picture. For IPv4 root sites, MPC is 1.86 times to 23.88 times faster than the baseline algorithms. Classification latency is under 0.1 microseconds. In terms of memory overhead, MPC continuously reduces memory usage by optimizing rule partition based on overlap analysis. Compared with existing methods, it achieves a better balance between memory consumption and lookup performance. For IPv6 root sites, MPC achieves 1.08 times to 4.3 times speed up over baseline algorithms. MPC achieves an average memory overhead reduction of 19.9% to 60.3% compared with baseline algorithms. In terms of dynamic adaptability, the MPC system requires smaller than 10 seconds to construct its structure for most root sets. Additionally, when traffic changes, the MPC system automatically reconstructs its structure to maintain stable performance. Our evaluation shows that MPC remains stable even under attack traffic. For distribution flattening, when low-frequency flows flatten traffic, Gini-based monitoring can detect it. For top key replacement bursts, when high-volume flows trigger shifts, the attack-aware mechanism prevents data structure rebuilding. In terms of network traffic detection, we also evaluated the performance of the sketch methods used in this study. The traffic driving stream summary (TDSS) structure proposed in this paper is referred to as TD. And we also compared it with other algorithms, Heavy Keeper HK and Cooker Counter, which is CC. The results shows that TDSS provides higher throughput and lower height for top K detection. OpenSwitch is an open source distributed virtual switch that optimizes the packet processing via a hierarchical multi-level caching mechanism. In this study, we integrated the proposal NPC system with OAS to enhance the Dataplane architecture while keeping the control plane unchanged. We also tested the throughput improvement after integration. When the extra match catch EMC is disabled, NPC OAS achieves a 0.13.01 times that of native OAS. Even when EMC is enabled, NPC OAS still maintains a throughput 10.71 times that of native OAS. To conclude, this study rethinks packet classification from a network-aware perspective. We designed NPC and it combines sketch-based traffic monitoring with packet classification. It leverages both traffic characteristic and route size features to get trace construction, enabling efficient packet processing. We believe this approach enhances the value of combining measurement with classification for an overall design and opens new direction for intelligent Dataplane algorithm. Thank you for your attention.
Okay, thanks for Boling's great presentation. So now let's move to the discussion part of this meeting. So we are very happy to have the first author, Xinyi, here to share her insights and experiences about this work. So does anybody online have questions? You can just mute and say it here and type your questions in the chat box. So then I can read for you. Yeah. Yeah, we have a quick question from Chao. Has NPC been compared with learning-based solutions such as narrow cuts?
Okay, I will answer this question. And NPC only compare with some traditional packet classification schemes like high-cast, hypercast, because our main idea is to bring the traffic pattern into the construction of the decision tree. So we do not use the artificial intelligence techniques. So we do not compare it with learning-based solutions such as neural cuts or other methods like this.
But yeah, so sorry, just to follow up that. But I never wrote papers regarding public packet classification, but I did read up a lot, in particular from Dr. Xie's group, like a class bunch NG, and actually that's how I first get in contact with Dr. Xie actually. So I think that all these paper works are very impressive, but still. I remember, I could be wrong, but I remember like NeuroCut claims that it can substantially improve the throughput because it can classify packets faster. I think that's essentially what it does, right? Or that's essentially what many packet classification works has been doing. So just from the perspective of throughput, or a memory footprint. Have you looked into like in what just out of curiosity, like in what settings could NPC outperform like neural cuts, and in what settings neural cards could potentially perform better. I just want to get to understand this. Yeah.
Okay, and from my point of view, and compare with methods like neural cards, our method is more lightweight because we do not bring the AI techniques. So for the construction of the data structure, our method is more faster, and it can adapt to the change of the network. And sorry that we do not compare the performance like throughput because we do not run their code, so it's hard to say our method or their method is better in the performance like this. Okay.
I see. Yeah, that's fair. I think yeah, sometimes the code could be hard to deploy, even though even though I mean I think like many paper has passed the artifact evaluation, but still to really make it run to be run on other settings could be a very challenging job. I understand that. Yeah. So, but I'm thinking, right? So I think the key insight, one key insight of NPC is that we try to measure or monitor or in certain way to sense or monitor the traffic flow so that we can adjust the way we classify packets, right? So I noticed that you the way you measured you measure the network is using Sketch.
Yes.
Could just out of curiosity, I know like a Sketch could be could be implemented in hardware or even in software-based switches more like it's easier. It can be implemented easily, but could we deploy like a reinforcement learning-based agent to do this traffic load measurements and then use this output to guide how NPC adapt the way it classify packets? Can you do that, or the design of NPC is heavily coupled with the sketch-based measurement?
Okay, thank you. And from my point of view, that is, the sketch is only a tool to collect the traffic patterns, and and if we can design other methods like artificial intelligence, something like that, and we can also collect traffic and predict traffic. So our method is not very rely on sketch, but why we propose this method is because some people do research on sketch, and some people do research on packet classification, but no one combine this together, and so we just utilize the sketch and try to get the traffic patterns from it, and that does not mean we can only use sketch, and we can also use other methods like artificial intelligence techniques to predict the traffic, not only to collect the traffic.
I see. Okay, now I understand. Okay, I have the I think I'm done with this question.
Okay, thank you.
Any other questions? Okay, now just let me start with a very high level question.
Okay.
Actually, I have done some research about packet classification at around 2018. So packet classification is actually a classical problem and was widely explored in past I think 25 years. So today, what do you think is the most timely and important aspects we need to resolve?
Oh, that is a very high level question.
Yeah.
And and I think that is because I began to do something like this from 2016, and I mean from past 5 years, and many people work on the many people try to optimize the performance with AI techniques. But for me, I think that I just say that it is hard to train the model or try to deploy it on the online system. So for me, I think a more important thing is to make it lighter and more easier to adapt to the network change, and more easier adapt to the traffic pattern and to the characteristic of the applications. And another part is some the DPU and other hardware techniques also can improve the performance of the network performance, and like IP prefix lookup and packet classification. And we also try to deploy our methods on some new hardware like DPU, and try to make it more and try to improve its performance and make it more intelligent by bring more things into the because the traditional methods usually make the data structure based on the rule characteristic, and what we want to do is to bring more information like traffic, like something to make the system more intelligent and to improve the overall performance of the system. But that is a very high level question. And
Yeah. I understand. It is pretty challenging to adapt the network traffic characteristics in the packet classification. So following this, did you encounter some implementation challenge when you implement such a solution in programmable devices?
Yes, because we try to implement it on DPU, but we just can use the DPU. We cannot design the DPU, so it is hard for us to get the information of the traffic and to make it directly to guide the construction of the data structure for packet classification. So I think the solution is to try to make a collaboration with some companies and to so for us, and I think the biggest challenge is that way for us we are hard to design the flow of the work. Yes, it works.
Yeah, that makes sense. So I think okay.
So sorry, Chang, I have another question, but maybe just a random thought, right? So I think again, this is a question for in general for package classification. So I think like in the area of network verification, in particular Dataplane verification, there has been I think Simon Lam from UT Austin, and his student gave this proposes concept called equivalent class, in particular on the Dataplane. I know it is a general term, but in Dataplane, basically equivalent class is a way to represent a routing table or a forwarding table in a relatively small number of rules. But I think they try to basically, for example, suppose we have a switch with maybe 32 ports, and then the flow space essentially, the action essentially is suppose there's no ECMP, right? There's no multicast, just a single forwarding. So the action can be divided. Essentially, there are only like 33 actions, right? Forwarding to one of these 32 ports, or just drop this packet. So that means we can theoretically use 33 rules to represent the whole forwarding table. And the way Simon and his student or Hong Kun has been encoding this equivalent class is to use a data structure called the BDD, binary decision diagram. And since then, I think in the along the line of Dataplane verification, many papers like APKey from Peng's group, and also like a token from our group, we have been using this BDD as the underlying data structure to encode equivalent class. And also, I think Peng also won the outstanding paper from NSDI this year, proposing a new variant of BDD that could encode equivalent class in a more efficient way. So I'm just wondering, can this BDD-based data structure be used for packet classification as well, or essentially they're the same thing, or people has already explored that and think that's not a good idea? I know this is a very general question, but because Xinyi has been working in this area for quite a long time, I figure I just ask for Xinyi's opinion. Yeah.
I'm sorry. You mean the BDD-based method? And sorry that I did not read the paper, and yeah. I'm not sure.
Yeah. Sorry, I guess the question would be like, have you read the paper from Alex Liu's group? I think there's one called like a T10 razor, right? And also there have been some follow-up, right? So I think what they did is try to condense or compress a large set of forwarding rules into a smaller set, but equivalent. I think the concept of equivalent class in the Dataplane verification is trying to do similar things. So I wonder can we try to, if we compress a large set of forwarding rules into a much smaller size, like either using BDD to encode or using other data structure to encode, can it help accelerate packet classification, because essentially we have a smaller number of rules to track? Or is this essentially exactly the same thing packet classification has been doing?
Okay, and maybe from my point of view, and I think that's there's two directions for the work on the packet classification, and maybe the thing that you talk is to try to make the memory consumption more small with structure design, and trying to compress the data structure, because the TCAM space is limited. But for us, and our work is on the algorithm that can be designed on the general purpose processors like CPU. So the memory consumption is not, I think it's not need. I mean that is not a big question, a very big question for the work that we now work on, and that are two directions, and we try to make the classification performance more high, but they try to make the memory footprint more small. And I think, but maybe we can also bring the traffic pattern when we try to minimize the memory footprint of their work. But I think for TCAM, maybe that is a big challenge because it is hard to bring the traffic pattern from maybe we need to get that from the control plane, and we need to use this information to guide the rules when they insert into the TCAM. But when the TCAM needs updates, and it is hard to update the whole data structure because maybe there is a very high consumption when we move the rules in TCAM, and that is not very flexible when the rules are updated.
I see. Yeah, I think okay. I think I have a better understanding about the difference between these two sets of work. But I will try to talk to you about that later. Maybe after this meeting.
Okay.
But I think there's another question from the chat. I think it's from Chen Xing, right? Yeah.
Yeah, let me just read it. What type of DPU did you try to implement just out of curiosity?
Okay, and this is still I mean, we are still trying to work on this, and we before tried to use the Bluefield, the DPU to try to implement our method, but we are still working on this.
Okay, I have some experiences on Bluefield DPU. I understand that I understand that for DPU it is not easy to directly program some adding some programs on its data bus. Actually the onboard CPUs are always utilized for control plane.
Yes.
Okay. Well, we got another question. Given that network traffic patterns are dynamic and can change rapidly, how does the NPC system adapt to these changing traffic patterns?
Okay. And in our work and our work, the NPC tracks two things. Not only the traffic, but also the rule sets. And for the rule sets, and we just count how many rules are added or removed from for a given time window. And if too many change, and we rebuild the lookup structure. And for traffic, we compare the top key flows between two windows, and if the heavy hitters look very different, and there's a sign that that we need to rebuild the data structure. And for updates, and we use an A/B switching strategy. And in this design, and one tree remains active for lookups while the other is rebuilt, and ensuring that the packet processing is never interrupted. And this approach also eliminated the risk of the packet loss and avoids the performance degradation. And the reconstruction process completes within a few seconds. And so we use this method to adapt to the dynamic of the network changes.
I missed the answer for the question, which DPU you are using for this project.
We tried to use the Bluefield, but we are still working on this.
So you don't have an implementation of this classification scheme?
Yes, in this paper we do not implement it with DPU. We only try to we only try to implement it with Open vSwitch.
Open vSwitch.
Yes.
Okay. And my second question is, how much energy is used by this new classification scheme? Did you look at the energy efficiency or energy consumption?
Sorry, and we do not look at the energy, and we measure the CPU cycles in our paper. And let me check. Oh, sorry, that's maybe we only measure the CPU consumptions of the other modules, like the traffic mirroring module and the rule set analyzing module, and we do not measure the energy in efficiency of the packet classification module.
Okay. So can you send us the slides?
Okay, sure.
I can. How you send it? Can you put it in Dropbox or share the folder that we can access the slides?
Okay, sure.
Or I can send. What is your email address?
My email address is I can.
Put it in the chat. Yeah, put it in the chat, please.
Yes.
Yeah, please just take a look at the chat box. Yeah,
Yeah,
Hersham,
sure.
do you have any other questions?
No, thank you.
Yeah, cool. Yeah, following Julian's question, I'm just curious, what is the overhead when you adapt to the dynamic traffic patterns? Is there any trade-offs? Yeah,
Okay.
is there any trade-off between the overhead and the let me
No.
see. Yeah, the dynamic characteristic.
Okay, and for us, I think the overhead is low because we for us the data structure for the construction is only for less than 10 seconds, and so the construction is very fast. And another part is that I think how that depends how we design the data plane, and if the data plane already has a sketch, and that is not attributed to our system because we only leverage the information it provides. So on the other hand, and in our work, we also design some things to reduce the overhead, and instead of the accurate value like the counting sketch, we only track the frequency ranges, and that reduce the update overhead. And we can also further use some sample methods to try to reduce the computation resources. And our experimental results in paper also shows that even under sampling, the impact on the classification accuracy and the performance remains minor, and this ensures that our framework and can achieve a good balance between the efficiency and the scalability.
Okay, cool. Yeah, my takeaway is that what kind of the traffic monitoring methods are used here, MPC can still get a better performance compared to existing work, right?
I'm sorry. Do you mean that the traffic monitoring method in our paper can get a better performance than the
I mean
existing
MPC, yeah. I mean the actually the performance gain of MPC is from traffic monitoring, right?
The performance gain of NPC from the traffic information that guides the construction of the decision tree, because we use the information to
I see.
yeah yeah.
I see. Yeah, so what is the what contributes the most to the performance gain?
The contribute most is we can when we utilize the traffic pattern, and we make the popular we make the popular packets that can be accessed from the more close to from the roots. That means we can reduce the memory access by using the traffic information to guide the construction of the decision tree and to reduce the memory accesses.
Yeah, cool. Okay, any questions from the audience?
So another question is still since package classification has been a very classic and well studied area, so what do you think would be the next step? Like what's after NPC? What's the next big thing you think?
Yes, for us, and we want to try to redesign the whole data plane, because the previous work only work on sketch or on packet classification or only on a single part. And what we want to do next is to try to bring the information together and try to use this information to redesign the data plane by making it aware of traffic pattern and the characteristic of the application, and to make that more intelligent. And we also will use AI techniques to try to predict the traffic and predict some other informations, and that is our future work.
Yeah, that sounds very exciting. I think I really look forward to that. Yeah, but for this work, like what is like the most challenging part you think for during your work on NPC?
Yes, for our work, I think the most challenge is to how to make the whole system lightweight, and another thing is how we try to make full use of the traffic information, because when building the decision tree, we need to select the dimension and to decide which type of method we will choose. And we try to the challenge thing is how to bring the traffic information in each step in our work. Yeah.
Yeah, I think so to make the whole system be fully traffic aware, huh?
Yeah, yes.
Okay, that's I think that's still I think that even at personally I think this is a very old a little bit old topic, but still I think from time to time I think like every 5 years we see 1 or 2 package classification papers. I think like I mean, I clearly I didn't read all the SIGCOMM papers, but I think the last one I remember is neural cuts.
Yes.
Yeah, and then the one before is I think there's a one from 2014, right? So I think called 6-pack or something. I forgot, but I think that yeah, I mean, work on PC is really not that hot and popular, but so I really admire you and Dr. Xi's dedication to work on this area with such technical depth. I really admire that.
Thank you, because we are very surprised that we can also write this paper to SIGCOMM. Yes.
I mean, yeah, the paper is really well written. I don't think I attended the talk during my stay at in Canberra, but I did quickly skim through the paper before this meeting. So I think
Thank you.
it was very well written. Thanks.
Thank
So,
you. Thank you much. Thank you.
So what could be the if I'm just so we asked about what will be the future and what will be the most challenging part. But if suppose you are a quote unquote malicious reviewer or attacker, do you see any you mentioned that you can measure the traffic change and then in certain way to help if mitigate DDoS attack, right? So is there from the other side, is there a way to bypass your mechanism? Could I still launch DDoS attack with even with your NPC being deployed?
Because we, to be honest, we add this part from the reviewers, and I think that the DDoS part is not the work of the packet classification, and so for me, and I think our work is only to try to detect the DDoS attack for they replace the top K flows, and we are not able to resist against the DDoS attack because I think that is not the work for packet classification, and not is for the work that the part that we work on. It should be something like firewalls and the other parts of the work, but we can only detect that to not make the packet to degrade the performance of the packet classification, but we cannot resist it.
I see.
Yeah,
and,
I have a
go
question.
Go ahead.
So, why don't we use GPUs to accelerate packet classification?
You mean DPU?
No, GPU.
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 To accelerate the classification.
Because I think that is two directions, and we do not work on the GPU. Maybe the idea can bring that into the packet classification on GPU, but we do not work on that because maybe there is a little something that we need to write the code on the GPU and to make the design, the specific design for GPU, and but that is a direction like we can bring the traffic pattern into the GPU like our TCAM or FPGA, but but for us, and we do not work on that. Sorry.
Okay, so in a nutshell, as we all know, there are many packet classification algorithms out there. So what makes your algorithm distinguished from any other algorithm? What makes it unique or no?
Yes, and for the other algorithm, they only build the data structure based on the characteristic of the root sets, like some old methods like high-cast, hypercast. They try to find the characteristic of the root sets and try to improve the performance. And our work is different from that, based on we bring the traffic pattern in our work. That is, the traffic distribution is highly skewed, and maybe 18% of the packets can match 20% of the routes. So we try to make these routes more close to the root node and to reduce the memory access. Okay. And that is the difference.
Yeah. Can you, how you handle encrypted packets? How you
Oh, sorry,
classify packet, which is encrypted?
we do not handle the encrypted packets.
Okay. Okay. Thank you very much. Great work. Thank you very much.
Thank you.
Yeah,
Thank-
handling. I think handling crypto traffic could be will also be one piece of interesting future work, right?
Yeah,
Exactly.
yes.
Exactly.
Yeah.
Both accelerating classification as well as handling encrypted traffic is something good for future work.
Exactly,
yeah.
Hashem.
Yeah.
I fully agree. Yeah.
Yeah. Thank you very much. This is great presentation and great paper. It is one of
Thank you.
great SIGCOMM papers. Thank you very much and have a nice day.
Thank you.
Thank you. Okay, I think time is up. It's nearly 12 o'clock. So let me just ask the last question. For a new student who is not very familiar with this field, for example, classification, so what do you think would be the best way to get started?
I think the best way to get started is to read the source code like OpenWay Switch, because in OpenWay Switch it uses the tuple space search, a very classic packet classification scheme. Although that is not related to this paper, but for me, I think maybe the best way is to know the system, how it works, and because how the packet is received and it is faced and is processed and is looked up in the hash tables, and that is the best way to get started.
Yeah, cool. I think another benefit to use OVS is you can just perform some experiments on your laptop, right?
Yeah.
Okay, cool. Yeah, so yeah, we are coming to the end of today's meeting. We have a big thanks to Boling for the wonderful presentation, and also to Xinyi for joining us and sharing her insights. This paper actually brought up a lot of interesting points and sparked a lot of great discussions here. So it definitely gave me a lot to think about. Thank you all again for joining us, join today's reading group. We'd love to see you again in our next SIGCOMM reading group. Yeah, all right. That's it for today. Good night and have a good day. See you next time.